Okay, I think we can start. So welcome back to the second lecture of the course. I hope after the first one, you had a better idea about what is mathematical programming. At least you started to see some problems, how to model that. And today we will continue with another topic that is mixed integer linear programming. That is basically the second step, I will say, where some of the variables of your problem can be integer. Can you see? Is everything fine with the presentation? Just checking.
Yep.
Okay, great. So let's start with this. And today I also have this tool that I think is quite nice to write. So last time we had a few problems with the tool included in Zoom, but this is better. Okay, so what is a mixed integer linear programming problem, or MILP? You will find this MILP many times when you go through optimization problems. So now you know that it means mixed integer linear programming. And basically, the structure is exactly the same as last time. So this thing here, the only difference is this. Now, some of the variables are integer, okay? Meaning to say, this can take any value, 3.5, 93, whatever it is. This one can only be integer variables. Can be negative, positive, it depends, but you may think that is not a big difference. Actually, in terms of resolution, it will make a big difference. Just to share with you, linear programming is known to be P. I don't know if you are familiar with the complexity class, P and P. And MILP is in the MPL, so it's much more difficult to solve a mixed integer linear programming problem. But Cplex can still do that. So this is a graphical interpretation. Imagine that we have a problem where we have a few constraints. So this is the x-axis, okay? This is the y-axis. And this, let's say that this is 3.5. Okay. Now, the area inside here is your feasible region that is determined by 4 constraints. Okay, this one could be something like x less than or equal to 3.5. So you can take only values lower than this, right? So this one here could be what? Well, it seems that here y greater than or equal to 0, right? And for this one, x greater than or equal to 0. And then we have the fourth one that is this. Actually, this should be less than or equal to. There is a mistake, I guess. But the idea is that if you look at a linear programming problem, the feasible region will be this whole area here, right? Why? Because it's the area identified by the constraints, and because the variables can take any number, any value, all these are possible solutions. But what happens when you say that x and y now are integer? Now, what happens is that instead of having this area as feasible solutions, you only have these black dots. So only the integer values. So then you may be wondering, okay, wait a second. You said in the previous slide that solving integer programming is much harder, but if you look at the picture, it seems that the number of choices is actually lower. So how come it's harder to solve a mixed integer linear programming? The reason is, just to cut it short, that when you solve a linear programming problem, you can prove that the optimal solution is one of the vertices of your feasible region. So you actually don't need to explore what is inside. And there are some algorithms that allow you to explore the vertices and find out the solution. Whereas for integer programming, any integer number inside here, any integer point here can be a solution. So even though it seems at the first look that linear programming is more difficult because you have more solutions, actually integer is harder, and is solved with different methodologies. Some of them are like called the Gomori cuts, where you try to cut some fractional solution and then look at what is inside. Others are called the branch and bound, where you split the feasible region until one of the vertices is integer. Maybe you get something like that, you know. But we are not looking at that in this course. This is how to solve the problem. For now, we know that to solve the problem, we can use Simplex. There is a software, because we are looking at how to model the problem. So remember the diet problem last time? It was the problem we solved together, and it was the problem where we had to look for the amount of items to buy. We had 3 types of food in this example. We had bread, beef, and fruit. And then we wanted to satisfy some requirements in terms of nutrition. So we had the vitamin A, vitamin B, and proteins. And we wanted to minimize the cost. And if you remember last time, when we found the solution, so this is the model, that was the optimal solution, right? And that was the solution in terms of number of units of beef, bread, and fruit. And the question was, wouldn't it be more interesting, like useful in practice, if these were integer numbers, assuming we can buy integer units of bread, beef, and fruit? So how to do that? We can use mixed integer linear programming. And I show you how. It's very, very easy. What you need to do in the model is just this. You need to say to Simplex basically that the variables you are considering are integer. And to do that, you just need to write the keyword integer. And that's all. So it's very simple. Even though behind the meaning of this keyword means that Simplex is using completely different algorithms to solve the problem. As I said, there are branch and bound, Gomori cuts, branch and cut, many other things. But for us, the big difference is only this keyword, okay? So when we say something like that, we are saying, well, now the variables can only assume integer values. And then what happens when you solve the problem? Well, you get the solution. And you see that now the numbers are integer. I want to mention something here. Last time we said that whenever we put more constraints, we expect the solution to be worse. And integrality constraints, meaning to say specifying that some of the variables are integer, is putting more constraints, right? So again, we are not surprised to see that the value of the objective function is worse. We wanted to minimize the cost. Before it was 26.69 or 7, now it's 26.8. Okay, and you see also the outcome is different. Now Simplex is telling us integer solution, right? Optimal integer solution. And you see that is mentioning branch and bound. That is the algorithm that I was mentioning earlier. That is one of the ways you can solve integer problems. Okay. Okay. Let's look at the example we had before. This one, again, is not equality, is wrong. But let's say that the feasible region is this area inside here. Now, if you solve it with linear programming, so let's say that the variables can be anything. And let's say that the objective function, for example, is this. You will find out that the optimal solution is here. And as I said before, is not a coincidence that the optimal solution lies in one of the vertices of the feasible region. But if you look at the integer solution, you find that actually it's here. Interesting, because first of all, you will notice that the integer solution is not the closest one to this. Like you may have expected, well, if this is the optimal linear, maybe the integer is here or here. Actually, it's quite far. And you can have very interesting problems where the linear solution and the integer solution are really far. Okay, so that's why some people may say, hey, if I have an integer problem, what happens if I remove the integrality constraint and I solve the linear relaxation? That's how it is called. Well, sometimes the solution is very close, like the values are like, you see here is 0.1 difference, but sometimes you can find really, really, really different solutions with objective function values that are quite different. So that was just to give you a graphical intuition on what is mixed integer linear programming. In this case, all the variables are integer, but in general, it can be a combination of integer and linear and continuous, sorry. And at the same time, this is actually what I want to share with you about this. I don't want, again, to go into the details of the resolution strategy because this is not the objective of the course. For us, the objective is first to understand how to model integer problems. And you have seen, we just need to specify a keyword, no big deal. But the other thing is how can we model integer problems? Because especially in the next lecture, you will see we deal with binary. Binary is a special case of integer where variables can only assume values 0 or 1. And that's very interesting when you want to model logical condition like if, then, or things like that. Okay, this time, as you may remember from last time, I say that we have a homework. So I reduce a little the theory part because, again, that's all I want to share with you about integer linear programming. Really, if you have questions later about how to solve the problem, what is the algorithm behind, we can talk about that. But for now, again, this course is more about practice. So that's why I want to focus on that. If you don't have any questions, I will jump to the session where we work together. Then we can have the pause, and then you can have, like last time, a few questions that you can work in the breakout rooms. I assume you have downloaded from the website of the course the material for this lecture. If you have not yet done so, please do it before we move to this part. And at the same time, you will have realized if you check the website that I have uploaded the video of the first lecture, the slides, and also a cheat sheet with the most useful commands in AMPL. So you can have a look there. Okay, so the problem we are working together today is this one, is a kind of assignment problem. We have some items and we want to assign them to boxes. Okay, the problem is like that. We have 3 items, 3 types, let's say A, B, and C. Okay, and how many items of each type? Okay, for type A we have 3, for type B we have 2, and for type C we have 2. So imagine this is the item that you have to send. Maybe you have to put into box because you want to ship somewhere. What about the boxes? We have also 3 types. We have type A, type B. No, sorry, this is again about the items, or the boxes is below. The items A, B, and C, they are different because they have different volume. Okay, so the type A items, they have a volume of 0.3 cube meter. I mean, the numbers are just invented. It's not really important. For those of type B, we have 2.3, and those of type C, we have 2.5 cube meter. Okay, so this is about the items. What about the boxes? We also have 3 types of boxes, type 1, 2, and 3, and each box has a capacity. So for example, box 1, this is the capacity, 5 cube meter, then 3, then 1. And also we have a maximum number of available boxes to use. So for type 1, we have 3, for type 2, we have 2, and for type 3, we have 5. Okay, let's stop here for a while. What do you think all these things that I have highlighted here, what do you think they are? Remember that we say that in optimization problem, mathematical programming problems, we have objective, variables, parameters, and constraints. So all these things are basically parameters. They are the data of your problem. Okay, remember, parameters are numbers you know before solving the problem. So what is the task? We want to write an integer programming model in AMPL, okay, where we want to minimize the number of boxes required to pack all items. So minimize the number of boxes seems to be the objective, right? And we need to pack all items. These basically will yield to some constraints. Because to pack all of them, we will have to respect some volume constraint. We will have to make sure that all of them are packed and so on. And then we have also another thing here. to make the problem a little easier, we say that boxes of the same type can be combined to increase capacity. So for example, if I put together two boxes of 5 cube meter, I can have a capacity of 10. And I can use 10 cube meter to put, for example, these 3 objects, right? That will not fit otherwise. So we don't look here at, oh, can I split or I cannot split? No, we assume to make it simple that we can, the boxes of the same type, they can be put together to get a combined capacity. Now, this is a lot of information, so I made a picture to make it clearer. Let's say these are your items. So we have item A, B, and C. We have 3 items of type A, and this is the volume. And then we have 2 items of type B with the volume and 2 items of type C with the volume. And then we have the boxes, right? The box 1, volume here, and volume here, and this is the quantity. So what we want to do is basically to put these guys inside the boxes. And we want to minimize the total number of boxes that we need to use. Okay? Is there any question so far? No? Okay. Then I think we can go to the next part, where we are basically trying to move. Remember the first lecture, there was that picture saying that the first step is to understand the problem and basically understand what are the parameters, variables, constraints, and objective. And as I already said, all these numbers, the information I highlighted in the first slide, are the parameters, so the data. So we have the number of items of type A, B, and C, 3, 2, 2. So is this, right? 3, 2, 2. And then we have the volume for each of them. That is this information here. And then same for the boxes. How many boxes do we have? 3, 2, 5. So 3, 2, and 5. And what is the volume? 5, 3, 1 cube meter. 5, 3, 1. Okay. So this slide basically represents, these represent the data of your problem. Objective, we say, is to minimize the number of boxes we need to pack all items. What about the variables? Well, there are different ways to work to find a model for the problem, but in this case, I would say that we need to know 2 things. How many boxes we use, because this is also the objective, right? So we need to know if we use a box or 2 or 3, whatever it is, and then how many items of each type we put in each box. Okay? And finally, the constraints is that first, we cannot exceed the maximum number of boxes. So for example, here we will have somewhere something saying, hey, you cannot use more than 2 boxes of type 2 or more than 5 boxes of type 3. Then each item must be assigned to a box. We need to make sure that all items are assigned to a box. And then, of course, we also need to make sure that we are using enough boxes to guarantee that the items can fit. But all these will be combined in this model. So we go through line by line to understand what is going on, okay? So first thing is we need to define the items and the boxes. Remember, we defined the last lecture the concept of sets, right? And these sets are useful when we want to define later variables for each item of the set and parameters. So the first thing we say, okay, items here, we have 3 types of items, A, B, and C. And then we have 3 types of boxes, 1, 2, and 3. If you remember, this notation with these dots means all the integer numbers from 1 to 3. Okay? Then we have 2 parameters for the items. One is the volume and one is the quantity. So when I write VI of items, it means that there is a parameter VI for each item. So I will have VI for A, VI for B, VI for C. So here we are just defining the parameters because later in the data file, we will have the parameter values, okay? So what else do we need? Well, if we look at the picture here, for the items, we need to know how many we have and the volume. So the quantity and the volume, okay? So what about the boxes? Well, for each box, we need to know the capacity of the box and the max quantity that we have available. That is basically, again, what you see here. How many boxes and the capacity, that is this information, okay? Great. Now, what about the variables? Well, the first one we define in these slides, we say how many boxes, okay? So the number of boxes we use is a variable X, I call it X, and we have one for each box. So let's say X of 1 is the number of boxes of type 1 that I use. So this is an integer variable because we cannot use fraction of boxes. Is greater than or equal to 0, and see that each condition can be split by a comma. And this is also important. We cannot use more boxes than what we have. So if you remember, this guy here is the maximum quantity of boxes we have. So when we write that X of B is less than or equal to this, we are basically saying, look, you can use 0 or more boxes, but no more than this. And this parameter is the max quantity we have. So is it clear so far? If it's not clear, you can stop me anytime, okay? No question? Okay. So what about the second variable? Well, here, this is the one that we use to assign, right? So here, I call it Y, and you see that we have two indices. For each item and for each box, we have a variable. So what does it mean? So here, basically, what we want to do is basically answering to this question. Oh, let me remove this first. How many items of each type are put in each type of box? So for each item and for each box, I will know how many of these items type A are put in the box B. So again, it's an integer number greater than or equal to 0. And of course, we cannot exceed the maximum number of items. So I can say, look, item A, I put 3 of them in box 1. And then I put 2 of them in box 2, whatever it is. But of course, we cannot put more than Qi of them, because this is the amount we have to put. Okay? Now, if we go to the objective function, what we want to do, we want to minimize the total number of boxes we use. Well, the variable X is telling us exactly this. So how many boxes we are using, right? So if we sum this is the total number of boxes we are using, and this is what we want to minimize. You remember this notation, sum, the sum of something like B in boxes and then X of B is basically saying for each element of this set, you sum. So this is equivalent to sum B from 1 to 3 of XB. Okay. And then what do we have? Well, for here we have a constraint for each box. So remember this notation, when we have subject to is a constraint, then we have the name of the constraint. And when before this we have this expression, it means that we have one constraint for each element of the set boxes. So in this case, we have one constraint for each box. So what is the constraint saying? It's saying, look, here we want to assign item to boxes. So for each box, let's say we are looking at box 1, you sum over the items these values, so the amount of item of that type that are in the box times the volume of the item. So this is the total volume of the items in the box, and this cannot exceed what? The number of boxes times the volume of the box. So what does it mean? If we go back to the picture, this means something like, hey, if I want to put, let's say this is 3, right? Let's say that I use both of them. So I have a total volume of 6 cubic meters. It means that inside here, let's say that I want to put this, I want to put this, and I want to put this and this. I cannot do that because the total volume of these is more than 6. So that constraint is saying that for each box type, whatever you put inside cannot exceed the combined volume of the boxes that we are using. Okay? So here, for example, we can put this and this is 5, and then that's all. We cannot put this. Last constraint is saying something different. It's saying that, look, when you have for each item type, you sum over all the boxes, and this variable, right, when you sum over the boxes, we are basically counting all the items assigned to the different boxes. And this must be equal to the number of items I have. So in other words, this means that each item has been assigned to at least one box. Because when we count all of them, we get exactly the value Qi, that is the quantity of items we have. Okay? Now, when we go to the data file, we have to specify the 4 parameters here, right? So VI, QI, CB, QB. And remember that VI and QI are defined for each box item, sorry, and CB, QB for each box. So here you see, right, the syntax like last time. For each element, A, B, C, in this case, because we are looking at the items, I have the volume and I have the quantity. And for each box, remember the set of boxes is 1, 2, 3. So for each one of them, I have the maximum number and the capacity. So the capacity and the quantity. So this is the data file. What about the run file? Like this is, okay, we have a question. Wait a second. Yeah, I mean, it's up to you how you want to define the set. You can, I mean, I use A, B, C, and 1, 2, 3. Sorry. I use A, B, C, and 1, 2, 3 to show you that you can use numbers or letters. It's up to you. I mean, sometimes, you know, when you are solving a problem, maybe you can even give names. Maybe you remember the diet problem, what we use. I mean, here I don't have the data file, but basically we call the food with their names. We have the bread. Yeah, I don't have it here, I think. But remember, we have the bread. Yeah, you see here, right? X was indexed by a set, and the elements were called beef, bread, and fruit. So it's really up to you what you want to use as a name for the items in the set. So we specify the model. Okay, we specify the data. We say that we want to use Cplex as usual. And then we want to solve the problem. And then we want to show the value of X and Y. So this is the objective. This is the output we got. And as you can see here, again, Cplex is telling us that we got an optimal integer solution. And branch and bound. You see, when you start to see these things, branch and bound and MIP, these keywords, integer, means that you are dealing with an integer problem. We got an objective of 3. And this is the solution. So the solution seems to be, we use 3 boxes of type 1. So the boxes type 1 were the 5 cube meter, right? So we use all these 3. And this seems to be enough to put all these items. So probably if we sum the volume, here we have 5, here we have 4.6 and 0.9, right? So it's 9.6, is 10.5, definitely enough to be put inside all of that. Okay. What about Y? So remember the variable Y was the this one. We had one for each item and box. So item A, in box 1, we put 3 of them. Item B in box 1, we put 2 of them, and item C in box 1, we put 2 of them. So you see, we are putting everything in the box 1, and as expected, because we are only using box 1. Okay, so far? So remember that now this seems maybe a little stupid because we are using just the largest box, but the thing is that we just wanted to minimize the number of boxes. And yeah, there is a point I will make later here, but if you look at the total volume, as I said, is 10.5. So we can use 3 boxes of type 1, and the total capacity is 15, so it's enough to put all of them. We can also use something else. So for example, imagine that we use 2 boxes of type 1 and 1 boxes of type 2, the 3 square meter, the 3 cube meter, right? And maybe we put, if we put these guys and these guys here, is 5 plus 4.6 is 9.6, so is enough to use just 2. And then maybe we can use these 3, we can put in 1 box here. So even in this case, we can use 3 boxes. What does it mean? It means that, and this is very important in optimization, you usually get an optimal solution, but it doesn't mean it's the only solution. We may have different solutions where the objective function is the same, and they are called symmetric solutions. Okay? So just because you find one solution, it doesn't mean it's the only solution. This is a very important point to make. Usually what happens is that the solver is telling you, hey, this is the, I mean, as far as there is a condition telling the solver, telling Simplex that this is optimal, it will not explore other solutions. But sometimes you may be interested in finding others. There are some settings where Simplex can show you a pool of solutions, actually. Or maybe what you can do, if you already know that you don't want a specific kind of solution, you can put more constraints. Okay, so for example, imagine that you want to use, you don't want to use, or actually, let's say that you know now that the best is to use 3 boxes, right? You know that. Now, if you know that 3 boxes is the minimum number, what you could do if you want to find another solution, you can say, oh, I want to use no more than 3 boxes as a constraint, and you can change the objective function. Maybe you want to maximize the number of boxes of, I don't know, medium size. So in this case, you already know that you will, worst case, find out the same solution as before. But if there is another solution where this can be used as well, you may find it. So that was just to tell you that don't think the solution you find is optimal and is also unique. There may be different solutions giving you the same value, so just be aware of that. For some problem, it's not the case. For some problem, it can be the case, and sometimes symmetric solutions can be one of the reasons why problems are hard to solve. Okay, because when you have many solutions, I just want to highlight that. Sometimes you find problems where, how to say, let me go here. So when you solve integer solution with the branch and bound, the branch and bound methodology is a kind of tree. So you solve a problem, then you split the region in 2, then you keep splitting, blah, blah, blah. And every time you are here, you have to solve a problem. And eventually this procedure create a tree of problems, and the optimal solutions are on the leaves. So what happens when you have a lot of symmetric solutions? This tree is very large. So the time to reach the leaves can be very, very big. So when you have symmetric solutions, sometimes this can really have an impact on the resolution time. And that's why there are some techniques where you may be able, with some constraints, to remove part of the tree, to make it infeasible so you can reach faster your solution. This is not really part of the course, but just for you to know why modeling is so important. Because when you do modeling, you can take this solution, you see that you have a lot of symmetries, you can put constraints that guarantee you find at least one solution, but many of the symmetric are removed. So you're just working on the modeling, and then the same problem can be solved much faster. Okay, so that's why I believe that modeling is really important. And that's also why I think that this kind of content, really working on how to model the problem rather than how to solve it, is very important. Even though knowing the basics of how the resolution procedure works is also important to better create an efficient model. Okay, do you have any questions so far about this problem or mixed integer linear programming in general? No? Okay, so now there is the part where you have to solve the question. We have two options here. Now is 3:40. So we can have the 10 minutes now, the pause now, and maybe come back at, I think we can have even 10 to 15 minutes. We can come back and then we can work on that. Or we can start now and then the pause will be included and then you can work during the pause, or up to you. So I would think maybe we can have the pause now so that we can start with the session. Is it okay for you? Hello?
Sure.
Yeah. So let's do this. We can come back at 3:45, I think. Okay. No, now it's 3:40. Sorry, 3:55. 3:55. Is it okay?
Yeah.
Yeah. So 3:55, then we work together on the problem. Actually, you know, right? I will split you in the breakout rooms. You will work on that. And then we will also have some time at the end to go through the homework and I explain to you a little more about how it works, okay? So see you in 15 minutes. Okay, I think we can start. In the meantime, any question? During the break, maybe some of you got some inspiration. No? So I hope it means that everything is clear. Anyway, okay, we have one. No inspiration, come on. Okay. So maybe we'll have inspiration during the session now. Same structure as before. So we have worked together the problem of assigning the items to the boxes. And now we have to solve two additional questions. So number one, we want to change a little the setting where now each box also got a price. So you see here, we have that boxes of type 1, each one cost $8. For those type 2, they cost $6 each, and type 3, $1. So remember, these were the largest, the medium, the smallest. What do we want to do now? We want to find a solution where we are minimizing the total cost of the boxes. So what does it mean in practice? It means that we have new parameters to define, because remember, whenever you see numbers, usually is parameters. So we will have to define some price parameter. And then the other change will be on the objective function, because now we don't want to minimize the number of boxes, but the cost, the total cost of boxes. Okay, so this means that here probably you will have to change both the mod file and the data file. The second one is interesting. So here, what we want to do is we want to change only the objective function, basically, okay? So you can say that this point here, you don't need to specify the cost anymore because it's not relevant. You can start again to modify the original model, and you just need to change the objective function. And now you want to minimize the number of the largest box, that is box type 1, that we use. So we want to use as little as possible of box number 1, type 1. Okay? This is more or less the idea for these two problems that you have to solve. So now what will happen is I will split you guys in the breakout rooms, and then I will give you, I don't know, I think I can give you 20 to 25 minutes, maybe 25, even though I think, okay, frankly speaking, the last one is pretty quick. The first one may be a little more, but both of them should not take much time. Okay, I mean, I didn't want you to work a lot in terms of giving you very, very complex stuff, because I don't think is the point. Here is more like practicing what we have learned, because now is with the homework that you will have more time to think about. I tell you already, homework is a little more challenging than these problems that you find here. But I think that's how you learn, you know, when you have to solve a problem that is not trivial and then you have to think about, that's when you start to develop these intuitions, you know, that later will be helpful when you solve problems you don't know how to solve. So let me split you guys in the breakout. And I think, yeah, we can come back at 4:25. Let me do that right now. Okay, so it seems that everyone was able to solve the problems quite easily. So we can quickly go through the solution. For the first one, what we had to do, as you have seen, was to create these parameters for the price of the boxes and then minimize the total cost. And basically what you need to do is to create a parameter here. The objective function is now this, right? The price times the amount of boxes. And then when you look at the data file, you have the new parameter here. So when you solve the problem, you should find, of course, yeah, the mod, run, whatever. The solution is 17. Some people found a different solution, I think is 0.25. The total cost is still 17, right? So that's also a way to say that symmetric solution can be found. You can have this different solution with the same objective and it's still a valid optimal solution. For the second one, you want to minimize the number of the largest box type 1. So what you want to do, you want to minimize x of 1. This notation identifies the first variable, right? Because box is indexed by 1 to 3. Okay. And that's what you should have done. This is the same. And then you find that you can actually use 0 boxes of type 1, that is also the objective function, and you are able to solve the problem. So any questions about this? I don't think so, because you were quite quick in finding the solutions, but if you have any questions, otherwise we can go to the last part and probably we want.
Can I?
Yeah,
sorry,
go on.
I have one question.
Yes.
This is not specifically related to this particular problems that we discussed, but in terms of minimization versus maximization problems. Now, I faced a time when like I used MATLAB and that only maximizes. So
Yep.
to convert that into a minimization problem, you could either like put a negative on the front, or you could do 1 divided by 1 plus the function, or many things, right? So which of these would be the best of any ideas on that?
well, if you do some fraction or things like that, you need to make sure that, you know, you may have division by 0 and things like that. Usually what I will do is that if you want to maximize a function f of x over x, right? This is minus mean of minus f over x. Usually this is the relationship.
Okay, thanks. Yeah.
Right. So what does it mean? Basically, if you maximize f or minimize minus f, the difference is the sign, right?
Yeah.
And then that's why you change it there. So this is the thing I will do.
Okay.
Or sometimes, I mean, then you have a variation. You can have the minus here and plus here, but it's more or less the same. So, I mean, you can also have fraction where you say, well, I maximize f or minimize 1 over some function of 1 over, but also these may give you a problem of nonlinearities and infeasibilities. The other option will be to use duality, but this is advanced. So duality means that for linear programming, not for integer, for linear, so for LP, when you are minimizing C transpose X subject to AX less than or equal to B, you know, this kind of thing, this can be converted into an equivalent problem where you maximize U transpose B, and these, I don't remember the sign, maybe negative. I don't know. There are some rules to change. But basically, this means that you can create another problem that is called dual, where you have new variables U, and you see that the meaning of the parameters that you have in the problem, like what you have in the objective function goes to the constraint, and what you have in the constraint goes to the objective function as parameter. So basically, the idea is that there are some rules to move from one to the other, and you can prove that if an optimal solution of this exists, this is equal to the optimal solution of that. So when is this important? When you have problems, just to share with you, since we have some time, sometimes you have to solve problems like that, min-max. So min-max or C transpose X, blah, blah, blah. So how to solve that in a single problem? If you use duality, this becomes a min-min, and this is actually a single minimization problem. So sometimes duality, so transforming max to min in this way is usually a good way to solve problem where you have this kind of min-max or even tree-level max, min, max, things like that. But in general, I would say if you just need to convert from min to max, is just changing the sign and making sure that you also, you change the sign of the objective function inside the min or the max, but also you need to change the sign of the result, like I showed you before, okay?
Yeah, thanks.
Great. So I think we can move now to the last part, that is the homework. Okay, first, how does it work? So this homework consists of 3 questions. What you need to do, you need to create a mod run, and data file is actually not required for this. And then you create a zip file with all these files and you send it to me. Okay. This is the format for the file, right? So it's 1 because it's homework 1. Then you have a dash question number dot mod or run. So for example, I say there are 3 questions. For the first, for question 2, the mod file will be 1 -2.mod. Okay. Inside the zip file, you also put a readme with the objective function value that you obtain for the 3 questions. Okay. So to summarize, mod and mod and run file for each of the 3 questions, together with this readme.txt, where you describe basically the result you got. You create a zip file, okay, and you send it to me by this deadline. So at least I have some time to correct, but also I give you some time to, I think like is 4 days should be enough. Then you were very fast, so I think you need maybe even less. And also another thing I ask you, please use these as objective for objects for the email. Otherwise, you know, it will be very hard to separate. And then this software we are using for the email, I don't like it. Sometimes, you know, the way all the emails are divided is very hard to find them. So just use the same object in the email if possible. How will you be graded? So if you can submit the file by the deadline, you get 10 points. Otherwise, you get 0. And then a maximum of other 30 points. So more or less 10 for each question. Depends on how, if the solution is correct and the clarity of the code. So for example, you know that you can put the hashtag for commenting. I suggest you do that to make the code clear. And also the bonus point of 10 points for the first person who can send the solution for all of them, the correct solutions. Okay. Why the score? Because later there will be a ranking. You remember the first lesson I say that people are divided into houses. You don't know yet which house you belong to, but all the members of one house will contribute to the score of the house. It's really like a Harry Potter thing. I mean, I like Harry Potter, so I wanted to implement something like that here. This is more or less the rule. I will post this online on the website together with the slides, but also as a separate file, okay? So what is the question now? This is the problem. Okay, let's go through it together. So you see here, there are 2 equations, but they are not equation with numbers. They are equation with symbols, okay? So what does it mean? It means that this guy will be a number, this guy will be a number, this is a number, this is a number, this is a number, right? So each of the 5 symbols is an integer number from 0 to 9, no repetition, meaning that if this is 1, this one cannot be 1, okay? Now, the number associated with each symbol is ordered by the appearance of the symbol, meaning to say, this one is the first one you see is the largest. This is the second largest. This is the third largest, the fourth, and this is the smallest one. Because you see them in this order, right? So what I explained here, the first one you see in the first equation is the largest, by the second one in the second equation, so on. So there is an order, okay? What is your task? So the 3 questions here, first one, you want to find the solution. So the assignment of the integer values 0 to 9 to each symbol, so that, of course, these 2 must be respected. Okay, so these 2 equations must be true. And you want to minimize the value of this guy. Okay. The second one, you want to find a solution that minimizes the largest number. The number 3, you want to find a solution that minimizes the sum of the values of the symbols, but you need to have this additional condition that the pentagon is an even number. So I repeat, you need to write a model where these 2 are respected, where each of these guys is a symbol, right? And this symbol is associated with an integer number from 0 to 9, no repetition. The order is that the first one you see is the largest, and this is the second, and so on. And then the 3 problems are find a solution that respects all these and minimizes the value of this symbol here, the one that minimizes the largest number, and the one that minimizes the sum of all these numbers, where with the condition that this guy is even. Okay. And I give you a few hints. Don't worry if you cannot solve these or some of these questions is fine. The really important thing is that you spend some time thinking about that. So don't say, oh, okay, too hard, like, I don't know how to do it. No, just spend some time, go through what you have seen so far. The other hint I want to give you is that if you have a number where you have two equal symbols, like this could be like 33 or 22, how can you write it in a linear way? Because we are looking at linear problems. So 33, for example, is 10 times 3 plus 3, right? So if you see something like that, you know how to transform into a linear expression. And remember, when I say it here, that we cannot, like, we need to have these symbols ordered. So this is the largest, second largest, and so on. Remember that we cannot use strict inequality. So we cannot say that X is greater than Y. But we can use these kind of inequalities. So how do you model a strict inequality? Only by using this. So then you have the second hint. You may add something here to make it a strict inequality. Okay. So this is the problem. These are a few hints for you. The last question may be a little more challenging. But again, the important is not to really be able to solve everything. If you cannot solve everything, it's still okay. The important is to practice. And I think this problem is quite interesting because you will have to model constraint, you have integer numbers, you have some conditions that may not be trivial. It's a mix of everything you have learned so far. Okay. Do you have any questions? No? Okay, so these, I will put the slides, the video, and also these last three as a homework assignment, okay? If you have any question about the rules here, you can write me an email, no problem. And that's all. So this is your homework, this is the deadline. You have enough time, I guess, to do that. And that's all from this lecture. I think we can end up here. Is a little earlier, but I think it's good. No need to stay here till 5 because I mean, you were quite fast in solving the problem and doing everything. So I think as a reward, we can finish this 20 minutes earlier. Is it okay? If you don't have any question, I will really stop here. Okay. Good. So thank you for joining this second one. The last one will be next week. So there will be like we can go through also the solution of this at the beginning, and then as I say, the last lecture next week will be about binary programming. So that's when we really start to use the potential of mixed integer linear programming to model logical conditions, like if, then, or things like that. Okay, so thank you again and see you next time.
Thanks.
Thanks. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Thanks.
Bye.